Hello everyone, welcome to Intellipaat's live webinar on how banks prevent loan defaults using data science. This workshop will be taken by Mr. Sumit. So guys, let's welcome Mr. Sumit into the session. Sir, over to you.
Awesome. So, hey everyone, this is Sumit. I am a senior data and applied scientist at Microsoft. I've been basically working in data science area for almost around 5 years, and I worked on majority of the industry problems that comes into machine learning, AI, data science, as such. Majority of my work highlights majorly involved, deploying, machine learning models at 300 plus million users applications and working on core products like GeoTV, GeoNews, GeoCinema, Savan, Microsoft Windows, and similar product to apply AI, machine learning, data science into them and make value for businesses. I've been also working in on various teaching areas to various one-on-one mentoring or one-on-one guidance of for data science experience to almost around 3 years now. And yeah, so that is about me, and let's start the session. Today we basically be discussing about loan approval prediction problem, which is one of the major use case by most of the out there in the market. So any of the financial insurance sort of companies, banking and insurance companies use loan prediction models to basically determine if someone is eligible to, for the loan that he's asking for, and what's the credibility, will there be any defaults or similar such cases, right? So these companies use certain data sets which involves details about a person, loan applications and all the other things that comes into their their description, like their income, the gender, what are the dependents they have, any other previous loan they have taken, any such similar case, similar kind of data sets that they have, right? So all of this data has been collected by these banking and insurance institutions, and they make sure that they use this data to make such predictions for about their clients who is looking to take loans from them. This helps companies save money because they don't want to make a default, they make less loan defaults, and this basically make sure they are as accurate as possible. So these models make a lot of value for them in decide taking those decisions on who to give the loan or who not to give the loan. So it's a very widely used industry. The similar concepts been applied to various other other areas, like understanding users portfolios, or similar other banking problems that comes into regular use case of of banking institutions, right? So the idea, core idea almost remains the same, right? Either we do this or either not, right? So it's that. So looking at that customer loan data set, you will find this is just a representative one, so you don't have to see, this is the only one, but just a representative one. A data set can be looked something like an applicant ID or whoever's applying for the loan, then which state residence, gender, age, race, uh, marital status, occupation, career score, income, and such cases, right? So this domain is a banking. Environment will basically look both Python and R, just to get an understanding, if whichever area you are comfortable with, either Python or either R. Task to be performed is basically this. So usually, whenever you approach a data science problem, there are certain steps that you need to go through before you start approaching a data science problem, right? So usually these steps need to be performed, keeping in mind the problem statement as well and whatever the requirements of it, and then also need to be performed as a form of an experimentation for that particular problem. So let's suppose if I say that I have this particular data set, right? I need to make sure that whatever the data that I'm inputting into my model, is basically the data is in optimal format, the structure is correct, the data is interpretable by the machines. What is mean by optimal format is the data set is basically the all the data, the data set is doesn't have any missing values. They are basically they're basically there isn't any corrupt data into that particular any of the rows which is not of English or alphanumeric. It could be of some other language is not processable by any of your a code or as such cases, right? And it should be structured nicely. That means there should not be gaps in your data, or there should not be columns or rows arranged differently, right? So it should be in a very structured format. It should also be making sure that the data types of each of your columns are of the right format that should be interpretable by the machine, right? So a machine interpret the English language if you import it directly, right? So it should be converted to ones and zeros, or at least numerical format, such that could be interpretable by the machine, right? So you need to do all sort of those things to make sure that is done, right? Similarly, you need to make sure that any kind of feature scaling or similar techniques to make sure that all your features are normalized, and any of the features that need scaling up or down are also being done. So that is also part of your data pre-processing steps, right? So let's just look what are the steps that in general being followed. So just look at the glance, have a glance at the structure of the data set, find if there are any missing values, then calculate debt to income ratio as it is a new column named DTI, right? So generally what happens is you need to basically look at certain debt to income ratio is nothing but how does for a particular applicants, what basically uh, is debt, and what basically is the monthly income this person has, right? So you basically look at debt to income ratio to define as a ratio of all the applicants monthly debt payments by the his gross monthly income. So uh, any lenders, like loan lenders, look at this ratio basically to decide whether to lend money or extend any credits, right? So debt to income ratio is important there. A low debt to income ratio, that is DTI, indicates that you have a good balance between debt and income, and and lenders want it to be low, right? So to be like generally the numbers, approximate numbers goes around like 35, 36 or such. But the lower it is, the greater the chance of getting loans or credit you seek, right? uh, Similarly, second is calculating a variable named loan decision status, where the value would be 0 if the loan decision type is equal to denied, else it would be 1, right? So we are basically converting this variable into a certain factor. So this basically that if it this is basically a predictor variable, where we're trying to predict this only, right? That if it's if the value is 0, I am basically denying the loan, right? If it's 1, then I'm basically accepting that particular loan, right? So then moving ahead, we have creating a data set, new data set named basically customer loan define, which would have these column numbers from the other data. So what we basically essentially need to do is understand which of the fields should we pick up and assign it to a new data frame. So we don't necessarily have to take every field to make use of it in our data set. We can basically take selected fields and making sure we are using them. Also, we can experiment on other fields to see if we are getting our improvement in our accuracy while we get the output after training the model, right? So this is a more of an experimental step, right? Then some of these steps that which are there, if you can see, are in either text format, right? So the text format could not be directly interpretable, so you have to convert them into numeric, like gender, marital status, occupation, loan type. These are the factors which has to be converted them to need to be converted into numeric values so as to be interpretable by the models, or whatever the processing needs to be done there, right? This is basically all is data pre-processing that you need to do with your data before you make sure that data is appropriately prepared and then can be used for any kind of modeling, right? Next steps comes as model building. Model building divides the data into two different tables or data frames. One is basically your train set, another is your test set, and the split ratio is basically 70%. That means I'm saying 70% of the out of the total 100% data, I'm setting 70% to be a training data and 30% to be test data set, right? I'll use my training data set to train my model. I'll use my test data set to evaluate how is my model performing on different data, just to get the idea about it. So training and test set, if you have already gone through some data science problems in the past, you would know, but if you don't, I'll basically repeat. So training set is nothing but it's the data which you are showing your algorithm to that this is how loan this is how the data is basically been there. And uh, out of all this data, the decision status is either 1 or 0. So in what observation is this 1, or what observation is this 0, is being learned by your machine learning algorithm. So if I look at any particular observation into this particular snapshot, I can basically say that this let's suppose this particular snapshot has loan distance status of 1, right? This particular snapshot, the fifth one, has loan distance status of 0, right? My algorithm should learn each of these signals from each of these features that I'm giving an input to it, and making sure that it learns in a good amount of data, right? So it should not be like 100 200 records and then you're training your algorithm over it. You would possibly find cases where the algorithm won't be performing well if it's trained on a very less data, while it basically tries to do prediction over an unseen data, right? So it should be in a huge amount of examples to make sure that the algorithm understand what is false and what is true, means what is 0 and what is 1, while learning from the data set, right? So this needs to be taken care while you're trying to train your model or build a model for loan prediction. That as much data as you have, the better it is, right? Second is you basically need to understand how you are dividing the data, right? What is the distribution of your data? Understanding the visualizing your data in each of these features gives us the idea about distribution of your data. Because usually what happens is you might possibly find out that cases where loan decision status is 0, right, or denying, is basically low, and cases where loan decision status is 1, that is accepting or approving the loan, is basically higher. That means, let's take an example of approval status at 80%, denial at 20%, right? The data is basically imbalanced. There's basically something is called imbalanced data set. An imbalanced data set is nothing but a data set where one of the class if there are two classes. When I say two classes, that means one class is 0, another class is 1 for loan decision status, right? An imbalanced data set has one of the class as majority class and one of the class as minority class. In this example that I gave it to you, the class that basically says 1, that means the loan, all the observations that has 1, which has 80% and they contribute 80% of the data set, is basically called the majority class. The class which basically has 0, that contributes 20% of the data set, considered as the minority class, right? In such cases, the approach has to be rectified, right? how will I balance my data set? Can I do oversampling? Can I do undersampling? Oversampling of minority class, undersampling of majority class. Can I use some other algorithms like SMOT, or similar algorithms that basically, or nearest neighbor based approaches to build synthetic samples? Synthetic samples has been, I'm creating samples which is like artificial samples or observations, right, using the existing data. So all of those things where the application of linear algebra or similar comes into picture, right? So that is something which you can learn about while learning about the course, right? So all of those things are basically comes into detail before we go through this implementation. So this is like an end implementation, but to go reach to this place of end implementation, you need to basically learn all of those areas before you go to that implementation. Those areas include some part of linear algebra, some part of probability and statistics, and whatever the mathematics statistics has required to understand the basics, or the underlying concepts behind doing all of that. So that is one area. Doing data visualization for each of your columns is also good, because data visualizations gives us the idea about how's my data being distributed, and do I need to do any of these tasks that I'm talking about, right? Do I need to oversample, undersample? Do I need to basically make sure that the data is normalized? And do I need to make sure that I need to convert my data such that the data is removing my outliers, or removing those cases which are basically disrupting my data and making it undistributed, or the deviating it from normal distribution, and all those things. So normal distributions is nothing but a bell curve, right? A bell curve, if you have heard of it, is basically nothing but a curve that basically looks like a hill kind of thing, right? Where I'll show you the bell curve when we basically do some data visualization or such. So that following that bell curve, that means the data is uniformly distributed, and it's appropriate to do any kind of model building and such. So you have to do all those tests before we move ahead. So in the model building part, as we divide the data, so is there any doubts up until now? Else we can basically move forward. Okay, let's move forward then. Yeah. So dividing, so any doubts you have, any questions you have, you should ask in the chat. I'll be looking at the chat periodically. So you might not get the answer immediately, but I'll be looking at it, and possibly I'll get it. Or, if you have liberty to speak on the mic, you can basically do that as well. So dividing the data set into train and test set, that we have already done. Applying feature scaling on all columns, train and test set, except the loan decision status column, because loan decision status column is obviously 0 and 1. So you can't do any feature scaling of it. So feature scaling is nothing but looking at what parameters or features are. What features are these columns? That is what is called as features, right? That applicant ID is one feature, race is one feature, marital status is one feature, occupation is one feature, income is one feature. So you need to do a feature scaling to make sure, or scaling up or down, or whatever normalization that you need to do, if it is required. It's not a necessary step, but you need to check if it's required, to make sure that whatever you are or whatever the data that you're dealing with is basically normalized, right? Then creating a new variable, applying principal component analysis for 7 columns and number of principal. So basically, the step C is specific to one approach. We'll also look at that approach in R. So this particular approach is basically, applying an algorithm, unsupervised learning algorithm called principal component analysis on some of the columns of train and test set, and using PCA, we'll basically able to get some principal component as 2, and then using those as an input to our machine learning model called naive based model on basically on the training set of that particular model. So this is to understand that this is basically an input that is given. So we'll be looking about understanding a slight bit about what PCA is, right, and how does naive Bayes work, and then giving us an idea about you applying them into the code, right? So
generally, this is one approach, right? There are multiple approaches to solve that same problem. We'll be looking those multiple approaches as well, while we basically going through one of the implementation of it. So here in this case, I've taken two implementation, one through Python, another is R, whichever you're comfortable with. If you're not comfortable with either of them, that's also fine. Just understand the concept, at least for now, right? So just to get the gist about what exactly we are doing. You don't have to understand each and every line of the code to just to make sure you call it that I understood everything. You just need to understand the concepts behind what we are trying to do. If once you are comfortable with coding it yourself, you will be able to understand what is being coded, or what is being how the approach is being built. But right now, if you're not comfortable with Python or any of it, it's just understand the concept behind what we are doing right now. And once you think you understand and you think this should be useful, then go ahead trying it yourself. And obviously we're there for any kind of doubts that you have, so feel free to reach out. That's not a problem. Then we basically use naive based model on the training set, then predict the values on the test set, and then build a confusion matrix for actual values and predicted values. So basically this machine naive based model, we'll basically be learning about it when try to implement. I'll just give us brief introduction of what naive based model is usually, and then we can basically use it over certain cases. Then predicting the values on the test set, that basically we have done a split of 70% on the top. So the test set is basically used to predict how does the my model machine learning model learned from the existing 70%, and see if it's performing well on the rest of the 30% that I split it before, right? So the prediction test set is just to evaluate how well the model is working on a real life use case when it's being deployed, let's suppose on the soft floor of a banking office, right? So let's suppose it's being deployed in form of an API or in form of website, where the person or the operator would add certain parameters, and he'll get the loan decision as 1 or 0, just to from those parameters, right? So the that and those scenario, in the real life scenario, we're trying to replicate that real life scenario using a test set. The test set is used to replicate that real life scenario, to understand that how well my model will perform in the real life scenarios, right? So that's why we take a test set, just to understand that particular situation. It gives a fair enough idea for us that it will perform with 70-80% accuracy or 90% accuracy, although the accuracy might go up or down depending on how the real life data varies with time. So how and as in the parallel, we need to keep improving our model to adapt with that real life data as well. Similarly, building a confusion matrix for actual values and predicted values. So confusion matrix is nothing but understanding what was the actual value. So actual value is the ground truth, and predicted values the my model is predicting. So if I look at these test set, the 30% of the data set that I'm predicting, that this should be 1, this should be 0, this should be 1, this should be 0, and such, I should understand that originally was it 1 or not, originally was it 0 or 1, right? And so let's suppose originally it was 0, that means the loan should be denied for this particular observation. For this particular applicant ID, the loan should be denied, right? But in reality, my model in predictions, my model are predicting that it should be given. That means my prediction is wrong, I'm losing in accuracy there, right? Similarly, if it says that this applicant should be his loan should be approved given his features and such, and it's a good loan to give, right? Then it's basically actual observation is 1. Then without seeing the actual observation, I'll try to apply my model on this applicant ID and see if it's basically what's giving. If it's giving 1, then my model is predicting correctly. Then I can use this model with to do the prediction for any of the cases where I don't know if the loan should be given or not. That means the actual values are completely missing, and I'm completely relying on my prediction values to give the loan to that particular applicant, right? So that is how you basically tries to use it in a real life scenario. and then you keep on improving. Like, just suppose if you have 80% accuracy, you're losing on 20% of the observations. You need to basically improve your accuracies to 95%, 98%, to make sure that you are basically predicting it right 90%, 98% of your people have 98% confidence over your model in predicting if the loan should be given to the particular applicant or not, right? So this is basically becomes important as we go along. So understanding the same thing, if you have any questions till now, you can basically ask on the chat, otherwise we'll go ahead. Yeah, so for the agenda for going through the implementation, we'll basically discussing few things, right? Performing data imports from various sources. So we'll be looking at certain. So we'll be basically taking up Colab as a Google Colab as basically an environment where we can implement this particular machine learning model for loan prediction. We'll be basically performing a basic EDA. EDA is nothing but exploratory data analysis to understanding what data set, what is understanding everything about a data set. What are this particular feature means, or this column consist of, what are this values this column consists of, how does the distribution of data within each of these columns, and such cases, right? Understanding outliers, removing noises from the data, removing missing values, and such cases, right? Performing data manipulation, any kind of data, changing from one format to another, or any kind of such cases. Then in implementing data visualization, just to get the idea about all the visuals or charts that we'll be making, like box and whiskers plot, or histograms and such, right? And then implementing machine learning concept for prone defaults. So before we go around, just to get understanding of where we are in our what exactly where we are in our all those buzzwords that you hear in the market, right? About data science, machine learning, AI, just all like combined together. People don't have that clarity usually. So this slide is just to give you an understanding about that clarity. What are we exactly doing, and where we are in that particular, or between all those buzzwords. So right, if you look, so we know computer science, right? Computer science is one of the fields in engineering. Statistics is another field in mathematics. Business expertise, like any business related work, like either like understanding how businesses work, or like a product management sort of roles, right? Under having that particular understanding about the business, on how business is going to utilize these models, or how does you think from the business perspective on what is important for the customer and what is not, and all those things, right? Then traditional software, machine learning. So this is like a Venn diagram where data science comes in the middle of it, and all of these data science becomes an intersection of all of these areas, right? So this gives us the understanding that to be a data scientist, you need to have some of the contribution from all of these fields. It's like a journalist sort of role rather than a specialist sort of roles, right? A specialist sort of roles would be like a software engineer who is good at computer science, right? Someone who's good at computer science would be basically a software engineer, because that's a specialist role. Data science is not a specialist role. Data scientist is not a software engineer, right? He's basically a mix of a lot of skills culminated together to become a data scientist, right? Similarly, if you look at a data scientist knows a bit about computer science. That means he knows how to code or program. A data science, computer science, or using fundamental concepts of computer science. That doesn't mean he's coding a website or he's coding an app. That's a different sort of that's also being used in computer science, but a data science doesn't do that. Similarly, statistics, understanding what are the statistics, what because whenever you're understanding data, statistics comes into picture, because statistics is all about understanding how's the data being distributed, what is the mean, median, mode, all of those things of statistics that comes into picture, right? And understanding all of the distributions, understanding the hypothesis, all of those things are basically covered under statistics. So you need to know a bit of a statistics, be at least 40-50% good in statistics to work with data, right? Similarly, business expertise, understanding the product over which your models being used into. What is the business objective that you're trying to solve through your model, right? How is this going to benefit the business? How is going to add value to the business? Comes under business expertise, right? So it's not you need a degree for it, but you need to basically have a good understanding of how businesses works and how machine learning and AI is being driving businesses across the world, across different companies. Traditional research, traditional software, machine learning, right? So machine learning is a field which is an intersection of computer science and statistics. That means it involved all of those algorithms that are built on the basis of statistics and being implemented through computer science. That means if I'm talking about, let's suppose, in your 10th class or 11th class, you might have learned about basic statistics, like if I want to calculate mean, right? If I want to calculate standard deviation, right? If I want to calculate median, right, of a data set, right? You basically apply mathematical formula. What I'm doing using computer science is I'm automating that whole thing. I'm putting that mathematical formula into a code, and I'm using that code for any time I need to use that mathematical formula. So if I need to calculate mean, if I need to calculate median, if I need to calculate standard deviation, I'll use that code library or module and into my code, and then get that particular value, right? Instead of every time writing that formula to get that value, because it's inefficient, right? You might be building a big system, and this formula might be a small thing in the as a very small component of that big system, right? I don't want to write the whole code just to get that formula implemented in form of a code, right? So I need to be I use computer science to automate statistics. That's basically the whole idea there, right? So that's basically how computer science statistics, when they combine together, you basically say it as machine learning. Similarly, statistics business expertise is basically traditional research. It's not traditional research is like market research or user research and such. So they use statistics, and they also have business expertise. So all those roles where user researcher role or market research roles, all of this basically use traditional research, statistics and business expertise. And data scientist is basically a combination of all of these skills. So you need to have a business expertise, you need to be good in computer science, at least a little bit, not being expert or having a degree as such, but should be good enough writing code, having object-oriented programming concepts, and good enough in making writing efficient code that work at scale as well, right? And having a good amount of understanding of statistics and such, right? So, and acquiring these skills is not an easy task. That's I won't lie to you, but it's not an easy task. But the point is, if you learn it, there's a huge demand in the market, because someone who has expertise in all of those things are basically, obviously, you would find a rare combination. This is a rare combination, right? But it's not difficult, right? I'm not saying it's impossible or you can't do it. That's a that's just that will be nonsense, right? But the point, there are people who are doing it, right? I myself, I'm basically a mechanical engineer, right, from Bits Pilani, right? And a mechanical engineer from Bits Pilani working in a field and possibly working better than my computer science peers can do it, then you can also do it, right? So that is what mostly data science is about. It's all about your passion and interest into the field, and how you can basically use that passion and interest to learn as much as you can by courses or by your own self-education and such. I mostly learn from self-education, right? So this and there are always courses and everything to support you with it, and they help you accelerate your journey. So it took me a while do it, because there were no courses available while I was basically starting into the field. Right now, there are tons of courses, so you can basically go through them and apply them, make use of them to accelerate in your journey. Similarly, introduction, basically, how does it do the basic processing work? Analyze, visualize, understand, build models. So analyze is basically doing data analysis, understanding how is the data distributed, making those line charts, bar charts, histograms, box plots, scatter plots, and all those plots that generally comes into it. So that all comes analyze and then visualize. So understanding how the statistics of your data is, and all of those things comes in analyze and visualize. Understand gives us the idea about okay, my data is normally distributed, I need to do this. Okay, my data is uh, not correctly distributed, or my data has missing values, my data is in a wrong format, my data is not numerical, and all of those things. That's basically understanding your data and making use of that understanding. That's basically getting insights from your data, not just about how the data is, what data, what insights that you can get for businesses to grow, right? So you might have heard of this thing, right, that uh, businesses are using data and AI to make decisions, right? So how do they actually making decisions, right? They're understanding their data, they're knowing that this my data consists of if I'm looking that my sales is usually coming from people who are of age age 30 to 40, right? If my sales is coming from people who are of age 30 to 40, then and their preferences are these products in my website. So let's suppose if I take an e-commerce website, and their preferences are these products. These products are usually belonging to three different areas. Like one is basically either clothing, another is basically like grocery, third is basically like, let's suppose electronics, right? And these are the major areas where these people from this particular age range are basically buying the products from my website. So if I can get the insights, I would know where to stack up my inventory. That means since I'm getting 70% of my sales from people who are of this age, and they're out of those 70%, at least 80% of them are basically buying from these three segments. That means I need more sellers in these segments, and I need more products in these segments, so that I can ramp up my sales in the future quarter, right? Well, how did I get this insight from? I get this insight from the data, right? I told my business that this is what I'm seeing from the data, that this is where you need to go forward in the next quarter, while getting more sellers and getting more products onto the platform, and your sales will go up, right? And if that becomes true, you have provided your value to the business. Now business knows that my data can make value for me, your value in the company rose up, because now you're providing insights to them that are leading them to grow their company in terms of sales, revenue, profits, and everything, right? So just a very simple example to understand how data can provide those certain insights. Then build models, right? People doesn't simply just see, this is a very simple use case. I understand from one dimension. I understand from one dimension that how does my sales there in this particular area, and this sales has been depending on age group and possibly the category, right? But there are hundreds of other factors also that my sales could depend on, that I haven't taken in that previous example, right? What happens in such scenarios when you have 100 of such features or columns? Like gender could be one, the like location could be one, right? Then income could be one. All of those features has to be taken into consideration before you decide what sales you could expect based on those current trends, right? So current buying trends from the user. So understanding that is basically about building predictive models. You basically predict that this will be the next quarter's sales, right? This will be the next quarter's sales, because in the previous quarter so and so observation of users been seen, and they're buying this many products, right? So if they're likely to buy products at this particular interval every 2 weeks, every 1 week, given that particular pattern or trend that my model has learned, this is the projected sales that you're going to learn, that you're going to get into the next quarter. So if this is the projected sales, you need to back up your inventory such that you can back up that sales, right? So all of those things are connected. So that means you need to have that this much inventory into a website so that you can basically meet that sales, right? So you can basically get that inventory model, set it up based on the sales that you're going to project in the next quarter using your machine learning model. So this is how your machine learning model is being fitted into a business problem, which is how do I manage my inventory? How do I make sure that I need more inventory because the sales is going to skyrocket in the next quarter, right? So all of those things has to be taken into consideration before before you make those plans, because that involves money, right? If I'm ramping up inventory, that means I'm basically investing in my business, right? And if I'm investing in my business, I need to get return of that investment. And if I'm not getting that return of the investment, how do I know if I get the return or not? I'll basically ask my data scientist, can you project the sales? Can you see if I'm invest this much in my inventory, and if there will be sales of that much also, that means I'm getting that profit that I should be getting from that inventory or not, right? So all of those things comes from understanding that particular data and projecting or predicting model, building predictive models over that, right? So, and any person with analytical thinking like to find patterns in data and are good with visualization can become data scientists. So that's basically a very simple, way of, long story short, you can call it as like any person with analytical thinking. Like, if you can think analytically about, if I think logically, analytical to understand that, yeah, and this is the situation out there. What is something that could happen, right? What is important for me? What is not? How's this going down, this going up? All of those calculations in the mind to just that's basically something called you can call it as roughly as analytical thinking, right? And basically understanding the patterns in the data, right? If you're good with understanding identifying patterns, not in the data, or basically even in the real world, right? Even if you go to an office, right? If you see that if you look at the overall structure of my office, I haven't seen my architecture of my office, but I know that my lift is in the center. While I go to the second floor, the left side of the floor is basically these kind of conference rooms, or these kind of office rooms are built, and left side and right side, both of them are basically finding a similar sort of pattern there, right? I didn't see a different conference room. I would see a similar structure of a conference room, architecture, interior architecture of their conference room in the left side as well as the right side, right? That means there's a pattern over which the whole architecture of my office is built. If you are able to understand similar kind of patterns, that means you're good at understanding, finding patterns in even the real world, right? If you look at closely, okay, this conference room is different. The left side of the conference room is right side of the floor has a different conference room, right? They're not same, right? They're different in architecture, they're different in interior designs and everything, right? That means there's no pattern between them, right? I'm able to understand that. So all of that basically comes as a part of understanding how good you are identifying those patterns. Then you are good with visualization. That means you can build, you can basically manipulate your data, and then you can visualize into form of a graphs, right? The graphs that you used to learn in your higher secondary or high school classes, right? All of those graphs, like building a line curve, building a bar curve, and building histograms and all of those things, how you can actually make use of them. It's just not about building visualizations, it's about how you can make use of them, what sense you are trying to get out of them is basically important. If I'm seeing an upward trend and then I'm seeing a downward trend into sales, how is that upward trend different from downward trend, and why I'm getting a downward trend after getting an upward trend, right? All of those questions should come from a visualization. That if I'm getting a downward trend, that means something is impacting my sales, right? Something is impacting my business. That's why I'm getting a downward trend. I need to find what is impacting my business. Can I find those parameters or features? Okay, what is impacting my business is some external factor. It may be, some election, or maybe, some war that is happening somewhere, or right, or some prices that are going up, because of which people have become very, very conservative, and they don't want to spend too much money buying things and all that, and that's why maybe my sales is going down, right? So all of that understanding of, domain about what drives people to buy your product, what drives people to raise up your sales, what drives people to take a loan, all of those things is basically an understanding of business that comes from business expertise, right? So as good you understand your business, possibly talking to people, talking to talking to folks who are basically product managers, or business people, business development people, all of those things, you get the idea that how this is how my sales being done, this is how my customers think, this is how my product is right now. So you get that overall understanding while you basically try to play with the data of that particular product, or whatever the source of data is, right? So that all comes as a part of understanding, as a part of being a data scientist. So it's a very interesting field to be go around. And yeah, possibly there's a bright future, at least for the next half a decade or so. I don't know about after that. But yeah, uh, uh, things change, and even more demand can come in the future. So what we'll basically doing in the code is we're performing data import from various sources. So here we'll just use one particular source like CSV, perform data operations, perform data manipulations, data visualizations, executing the program, and yeah, that is all. So investment in knowledge always pays the best true, right? So yeah, you can reach out to these guys. So let's jump into the code now. I think we have done enough theory, and I think we can get the idea about what is going on. So understanding the code gives us the idea about what exactly is the loan problem statement for a loan prediction and how we can use it, right? So if you have any questions, I'll check it out. No, no, okay, cool, fine. Let's get back to this one. So the problem statement currently is, so this I'll just introduce the code environment, right? So this is a collab. What is collab is basically is a Google Colab. So Google Colab is nothing but online website, collab.research.google.com, where you can basically just go and launch a VM. VM is like virtual machines, where you can basically get a RAM and a disk, like you can see in here. And this RAM and disk is being provided by Google for free to you. So you don't have to use your local computer. You don't know where to write my code, or you just need a urgent practice with the code. You just search on Google, collab.research.google, and it'll they'll give you this particular interface. You can click on file, and you can launch a new notebook, and you can reach here, right? And then you can just practice your whatever the code that you need to write here. So this is a great platform. You can use it on a phone as well, even run your code in your phone itself, because there's always a this thing that on the top that basically if you click your code starts running and all of that, right? And there are some pre-installed libraries and such, that those libraries are being useful while you basically code or use in your data sets, right? So Google Colab is a great platform for any kind of experimentation you need to do. But if you come into companies, you need to basically use write code in possibly places like Visual Studio or Jupyter Lab or Jupyter Notebook and such. That also could be used, right? Those are like but you still need to go to productionization to make sure you code is deployable. So at the end, what you end up with is .python file or .r file. So just that's basically going to go into a deployment. So these are all these ideas just for experimentation purposes. But as you grow in your journey understanding how these models are built, how to write these codes, you will basically get the idea on what to how the deployment works, and how that deployment leads to real business value and all those things. All of that comes in a part of a certain course that you need to go through to basically get to that particular steps.
So I won't take you to this step 10 when possibly you are at step 1, but I'm just giving you an idea or just about it. It's fine, totally fine if you're missed to understand something, but I'm just giving you a just to give you a broader picture rather than an initial picture, right? And you can always ask questions on the chat or anywhere on mail to these guys. So the problem statement currently is Housing Avenue company deals in whole home loans. They have presence across all urban, semi-urban, and rural areas. Customer first apply for home loan. After that, company validate the customer eligibility for loan. Right? Simple problem. Your customer applies for a loan, and their presence in all the areas. The customer applies for the loan. Company validates if the customer is eligible for the loan. Right? How does the company validates? Using these models, loan protection models. Right? So problem is company wants to automate the loan eligibility process in real time based on customer details provided while filling the online application form. These details could be gender, marital status, education, number of dependents, income, loan amounts, credit history, and all of those, right? We basically saw that data set in previously. We saw the data set here, right? So similar to like these kind of details, right? So to automate this process, they have given a problem to identify the customer segment, those are eligible for loan amounts, or they can specifically target these customers. Here they are provided a partial data set, right? So this is basically the data set is loan ID, gender, is he married or not? Does he have any dependents? And such cases, right? Similarly, education, self-employed, what's his income, what's his co-applicant's income, what's the loan amount he's asking for, what's the loan amount term he's looking to pay for, and his credit history, his credit score, and all of those things, and property area, loan status, loan approved, yes, no, in such cases, right? So this is basically how the data set is being distributed for. Now, I'll use pandas. Pandas is basically, you can call it as a data manipulation library, where I'll basically try to load my data set. I'll try to massage my data set, see, if I want to change the format, I want to change the content of it, whatever the transformations I need to do in my data, I can do all my transformations using pandas. So pandas is a good Python library. So this first we are basically looking into a Python implementation. Then if we have time, we can basically look into a R-based implementation. So Python is a great programming language. Mostly if you look into data science landscape, Python is used greatly. I mean, like it's like whole of most of the upcoming even developments and the existing development and the huge community around is all around Python. So it's great if you learn Python, because Python is a multi-purpose language. You can use it for web development, app development, but you can also use it for completely for data science. So it's like very, very popular in data science. R is also another languages, but it's used until advanced analytics or similar kind of scenarios, right? But there are also a lot of machine learning being done in R as well. So, but if you ask me which should I prefer first as I move into the field, I would say prefer Python. You will have you will be very comfortable expanding your portfolio, expanding your profile if you're moving in Python first. So using pandas, I'm using pd.read CSV pd.read CSV module. So when I say import pandas as PD, I'm nothing but I'm renaming pandas library as PD, and then I'm using whatever the modules inside this pandas class to to read my data, process my data, anything I need to do for it, right? So pandas class has this module called read_CSV, which reads CSV files, and the path for these CSV files is this. So right now, if I show you the CSV file, it could be in your regular normal local directory also. In this case, I have uploaded into this particular here. So there's a button that you see in the top right, no file selected. I can basically click on this and it will reach to my local this thing, and you can basically click anything and you can upload it. You upload your data set there, right? So I have connected my drive. So there's a thing like you can also connect Google Drive. You can see this symbol here. This IPyNB file, which is like IPython notebook file, is being uploaded in my drive from where I mounted my drive. So there's an option here where you can click, and your whatever the thing is there, like your IPython file or your dataset.csv dataset, if it's there in any of the folder, it's basically can be mounted here, and you can then select anything you want from here. So I have mounted my drive here, and you can see that all of those folders that I have, collab notebooks, it will automatically create this folder there, and you can basically all of these collab notebooks I have, and this is my data, like trainloan.csv, where I can see all my all the data that I have, right? What are the data? So let's look a bit on the data side. So all of this data is basically like loan ID, gender, married or not, dependent, education, self-employed, applicant's income, co-applicant's income, loan amount term, 360 days, 180 days, and such. Credit history is there or not, property area, semi-urban, rural, and such. And then loan status, like why is yes, I should provide the loan, no, we should not provide the loan to this person, and such, right? So this is the data set we are dealing with, which is CSV. CSV is like comma separated values, right? So which is like Excel only, but used majorly while you're working with data sets. So CSV is like a go-to format. So I'll just cancel this, and I'll keep that open. So I basically copied my path here. You can copy your path and just click this 3 buttons, and you can click copy path, and you can basically get your path and then put it here, right? And then I can use that .info module to basically get all the info about my data set. So I can I loaded my data set into data frame, and then I click .info, and I get loan ID, gender, and all that. So I can basically say that all of this English language, or basically whatever text is there, is basically considered data type as an object. Whatever be the number is considered as an int64. My applicant income is considered as int64, and all of these is like float. So we know that all those data types, right? So right now it's considered as float, which is basically decimal point numbers. So all of these, if you look into the data set until your self-employed, all of these are numerical, right? So even this dependence and everything, like they're putting in as strings. So that's basically so as a not numeric sorry, not numerical, the string based, right? So that's considered as object. Then applicant is invoice purely numbers. Then all of these could be in decimal points. So whatever be in the decimal point, it will come as either float or double. Usually float is preferred than double because because of some internal mathematical reasons. These are basically dependent on libraries usage and what they prefer taking input. So float, that's a float. Similarly, property areas, basically there's an English that comes as an object. Similarly, this is also an English alphabet, comes an object, right? You need to convert these objects and into either float or int or such, right? So that will be required. All right, so observations. We can see there are a total of 13 columns including target variable. All of them are self-explanatory. We can also see some missing values. Let's take stock of missing values and what are the possible values of categorical and numerical columns. So there are a total of 13 columns from 0 to 12 that you can see here. And the total observations here is 614 entries, right? So it's all this whole of this data set is 614 rows long, which is huge, which is considered a very small data set. When I used to work in the companies, we used to work on TBs of data. That means billions and billions of entries, like not million, not thousands, it's billions of entries. So like it's a very small data set just for illustrative purposes, but you'll get the gist of it. And this data set goes to like lakhs of observations and records, right? So but this is just to get the idea about how does it work. You can always scale the data set up. The higher the data, the bigger the data set you have, the more processing time your code might take, right? But there are tools that you could use to improve the processing time as well. So that's a far away story, but just giving you just idea about it, right? So then what we also see is we also see missing values. Let's take stock of missing columns. What are the possible values of category? So we need to find out if there are missing values into it, because if there are missing values into it, that can't be taken as an input to our algorithm. So you need to remove those columns or remove those rows which actually has those missing values, and we need to identify where there's missing values there. right? And we also need to find out which of them are categorical or numerical columns. So any columns that basically has certain categories, like gender has two categories, right? Male or female. Married has no two options, no or yes, right? Dependent can have multiple options, like 0, 1, 2, 3, 4, up to 10, right? There may be people who have 10 children, but I'm not counting them. So education, like either graduate or not graduate or such, right? Self-employed, yes or no. So these are all categorical columns. They are divided into certain categories that could be useful for and they're basically English language categories, right? So it could be like even numerical categories also, but they're categorical. Similarly, if you look at applicant's income, co-applicant income, these are numerical columns because it could be anything. Like this income can be infinite, right? Because between 5849 and 5850, there are infinite values, right? There's not just one difference. There are infinite values. Like it could be 5.49.1, 0.001, 0.002, 0.00003, anything, right? So these are like numerical columns, right? They don't have any category, right? Like unlike dependents, which has category, like either 0, 1, or 2, or 3, etc. Right? So we need to find out these numerical and categorical columns here. So what we essentially did is we dropped the loan ID, because loan ID is a column which is you can call it as a user ID or applicant ID, because there's no numerical columns, or there's no point actually disturbing that, because that's basically our main variable. That's how we'll identify each observation. So we don't have to do any manipulation there. Then categorical columns, we know that categorical columns in this case are gender, married, dependent, education, and such. You can also find categorical columns by code, by saying that whatever be the objects, these are basically I can consider them categorical columns, right? So in this case, you can see that all of these, or basically there are certain ways to identify if is this particular column is categorical or not, by looking at their number of values and based on the few categories that they have. Like in this case, loan term amount, right? Loan amount term is basically, in this case, can be considered as categorical, because either it's 1 year or 6 months or 3 months, depending on how much amount of loan that that company, that bank provides, right? Usually we see that those EMIs, right? Either those EMIs are 12 months or 6 months or 3 months or 1 month or like 5 years. So there's a very categorical thing that you can decide on, right? So I can call that particular column as a categorical column. So you need to understand and have that understanding over there, right? Similarly, numerical columns, we know that these are like 3-4 numerical columns that are there. So all those int, float, and integers are basically considered as a numerical column. So I can basically print those numerical columns, and categorical columns are separately. Now, once I have looked at my data set, understood this is how my data set is. So data visualization gives us an idea about how is my data distributed. How can I plot a certain column and then see that this column is basically distributed like this. This is to understand your data first. Before even doing anything, you need to first understand your data, because if you don't understand your data, you might end up trapped somewhere in the downstream in the process. Because understanding data is the first process, because understanding data gives us the insights about how the data being distributed, which particular variable is important, which particular variable is not important, and I can churn it out, I can move it out, or I can find interdependencies between variables, and all those cases that I can do. So understanding the data is an important part in a data science process, right? So I'm doing this understanding through data visualization first. So there are certain data visualization libraries like Seaborn, Matplotlib that I can use. So Seaborn is like one of the libraries where I'm renaming it as SNS. Matplotlib.py as another library that renames as PLT. Then using those renames PLT or SNS, I can use certain modules that are used inside these libraries to plot this, right? So if I'm use plt.subplot 4,2 figure size 12,15, right? So what essentially is happening here? I'm trying to plot each of these categorical columns. Then I implemented a loop here. That means I'm looping to this particular list, which is categorical column list. What is my category? This is my categorical column list. I'll pick each column from it, and then I do a plot for it. So let's suppose I pick gender from it. So the first loop I pick gender. Then I also put index, like I can put indexes like
using enumerate is nothing but it assign an index to each of the iteration. So if I say I'm picking the first this one, it'll assign an index 0 to it. If I'm picking this one, I assign an index 1 to it. So this idx variable that you see is nothing but the numerical index that is being assigned in every iteration. So 0 comma gender is being picked up in my first iteration, right? Yeah, so then basically I'm trying to get a row comma column out of it. So whatever I need to put it up, and based on it I can I can place my graph and such. So count plot and such and all of those things is basically done to count the number of instances within those columns. So if I say gender, right, so how many males are there and how many females are there in my data set can be put there, and how many males has loan approved status, that is Y, and how many males has loan not approved status, that is N. Similarly, how many females has the loan approved and not approved, that data set I can basically plotting here. So I'm taking X as categorical column, which is basically in this case gender, and train data is basically train DF, which is basically there in my this particular data frame. And I'm basically looking at the hue. Hue is nothing but loan status. That means I need to find out the so what this says is draw a count plot on hue loan status. That means count all these from the loan status column, which is basically this column, count all these variables, count all the instances which has Y, total number of Y's, total number of N for male, total number of Y's, total number of N for female, and basically in an axis, row comma column, which means basically at this particular place on my complete chart. So I'm basically, at this particular place, plot this particular graph, right? So I'm seeing that, I have almost around 350-ish kind of loan approved male, and almost 150-ish kind of loan not approved males. Similarly, females is almost around 75 females of loan approved, and almost 30-40 females of loan not approved. So I just get that particular idea on how this distribution is there in my data, that I'm seeing the maximum amount of loan applicants coming from the male applicants, and they have the maximum loan approvals data in my data, right? So what do I get from this? I get from this is I get this insight from this is majority of my loan applicants, majority of my loan applicants are male, and majority of those males are having loan approved, right? So if I just sum this up, like 350 plus 150, that is like almost 500. Out of my 500, 350 of my male applicants has loan approved. That is almost I can say 70% of them has loan approved out of the total male applicants that I have. Similarly, if I look at female applicants, 70-75 of them are approved, and 30-40 of them are not approved. That means I call it somewhere around 100 of total female applicants. Out of these 100 total female applicants, I see 70 or 70 of them approved. That means 70-75 of the female applicants has their loan approved, right? This is the data that I'm getting. But in quantity, my males are higher in terms of the female applicants. So in future, what I can deduce is the percentage of applicants getting loans is almost same for males and females both, but there are higher numbers of males applicants coming in to take the loans than female applicants. That means I need to target cases where I could basically say that I'll be getting more male applicants. That means I need to decide my strategy on how do I make sure that I'm able to get as much amount of male dominating data into my whatever the data set that I'm trying to build or create, or as such cases, or what are the attributes of such sort of data. So all of those attributes can be taken up, should be taken care while building up. So all of those things comes in data visualization, right? There are certain tools used in data visualization like Tableau or Power BI or multiple, or even simple Python based visualizations, right, that are used in industry. But Power BI is like one of the most prominent tools that have been used in industry, where you can connect your data pipelines, and then you can visualize your data, and that data keeps on updating every day, right? So you can basically see the regular data and those business reports that you can create, and those business report could be used by product and the business to make decisions based on the data, right? So that is one thing. Then, so similarly, married and non-married, so all of those distributions, similarly education, dependence, and credit history and loan amount term, all of this distribution can be plotted out to understand that particular that particular distribution for each of these columns, right, and see how the distribution been impacting each other. Similarly, what are the things about the data set? So we see that low loan approval status consists of about 2/3 of the applicants have been granted loans. Like we deduce, right, almost 70% of the applicants have been granted loans, right, in this case. It's from the first curve. Second thing we derived is there are men more than women, like approximately 3 times more than women, right? The 500 men, and the women is almost around 100 to 150, right? So almost around three times to 4 times that are there. Similarly, marital status, 2/3 of the population that the data set is married. Married applicants are more likely to be granted loans, right? So you can basically see that marital status from this particular curve, right? That 2/3 of the married people are getting loans faster than the non-married people, right? Or applicants. Similarly, dependents, majority of the population has zero dependents and are also likely to accept it for loans. So what I see from it is the applicants which have zero dependents are more likely to get the loans, get their loans accepted or approved. So that is also one criteria or insight that you can get, right? That they're less defaulters with dependents, and they're more likely to get their loan approved. So if someone tomorrow comes to me, or as a banking or possibly a loan manager comes to me and asks me, hey, this is the profile of this guy, tell me, should I give him a loan or not, right? I'll say, hey, I know an insight from our past loans, and we see that a very less amount of defaults from those profiles, and these profiles consist of these features. The features are the married people are more likely to married people with no dependents are more likely to a better loan customer than a married person with dependents, right? So that's basically a good insight. Check this, if this is the data set, then he will give to the loan manager, and loan manager take a decision possibly on it, right? So this is like a understanding data, getting insight, right? So only doing this process in the industry makes a lot of money for the data scientist. Why? That insight is so valuable, the decisions are so valuable. What does people at the top do in any company, right? What any industry, what does people at the top do? They make decisions, right? And the better the decisions they make, the better their chances of being having a higher approval ratings, and having better ratings into their company, right? Their decisions are going to impact the whole course of their company, right? So decisions are one of the most important thing for them, right? And how do they get to make these decisions? Because their experience, their 20 years experience, 25 years experience, and they're making decisions for the company, right? But right now, data science has given the power in the hands of common people to make decisions. Now, people who have almost 1 year, 2 year, very few experience can make decisions for the company based on the power of data. And data never lies, right? Data will give you the actual reality, and with that actual reality, you're making that decision. So people who have been making those decisions with their experience and gut instance from like 20 years can now be making decisions through data with someone who has been only just 1 or 2 years experience, providing insights to these people who have been basically of higher experience. And now these people are being dependent on those data scientists to make those decisions for.
right? So this becomes a great demand for those people who can help these people at higher up or higher management to make those decisions for them, right? So, and these decisions by data are possibly more accurate than the decisions made through gut instincts or just by intuition, right? So because data, I'm trying to get that actual proof. See, this is the reality. A gut instinct or intuition may be right, may be wrong. There's always a 50% chances there, right? It could be right, it could be wrong, right? But data gives you the reality. So you can making a decision through data is a more reliable way to do it rather than doing it through intuition. And what you're seeing right now, right in front of you, is one example of how data has been used to make those decisions, right? Similarly, education column, right? Education, about 5/6 of the population is graduates have higher proportion of loan approval, right? Similarly, 5/6 of the population are not self-employed in the employment loan applicants. Similarly, property areas, more applicants from semi-urban are also more likely to grant loans. Similarly, applicants with credit history are far more likely to be accepted, right? Loan amount term, majority of the loans are taken for 360 months or 30 years or such, right? So that's basically the idea that you get from this particular data, right? Now move to the processing that data and manipulate that data to understand how we can do a prediction for cases where I don't have an approval or I don't have that particular data with me, that like this loan status data, right? This is the data that is past data. I already have the history of all these applicant IDs who have been granted loans or rejected loans, and I also have this history of how many of them are defaulters and how many not of them. But I just want, this is past data. I'm just looking at the past data, getting insights out of it, and all of that is great, right? But what I also need is to predict. I need to know what's this loan status for tomorrow if there are 5 applicants coming to me in the bank, and I need to know that should I give them loan or not. I don't have this loan status now. So predicted models or prediction is done for future, that I'm trying to predict, hey, these are the applicants, these are their profiles, these are their all these attributes that I have for this new applicant ID that is coming to me tomorrow, and should I give them a loan or not, should I give him a loan or not, or her a loan or not, right? So I need to basically I'll use this predictive model based on my past history it has learned, and based on that past history it will try to do a prediction. Okay, shall I do what's my model saying? The model is saying he should not be given the loan, right? Now I'll look deeply into his profile, I'll do all those insights, see my model is saying not giving the loan. I am also with my model, because I also see similar applicants in the past not giving being our loan defaulters, I should basically not give the loan to this person, right? And then that is how the whole process slowly becomes automated, right? So right now, till now, the loan manager looking at the all this data manually, and then his previous experience, and then some recommendations from his branch manager or whoever is the a senior understanding, and then trying to provide the loan, right? And the loan is maybe like 2 crores, 5 crores, 10 crores, anything, right? And then they disperse that, but and with a high risk of maybe, I don't know if this person will default or not, right? But now I'm making that a decision from my model, right? Now that additional help the loan manager is getting is a support from past data, which he was not able to see it because of huge amount of data, and a support from model which is basically being trained and proven to be good enough based on the past decision that the model has taken. And then he's able to get a better help deciding should this person be given loan or not, right? So that is how machine learning is adding value to the banking industry through a simple loan prediction model, right? So as we go around, let's analyze the numerical columns. So we have only analyzed, these are all categorical columns, or columns which has some text or something, right? And which has some categories. Now let's also look at the numerical columns. Numerical columns are, what are numerical columns in this case? we have applicant's income, co-applicant's income, or loan amount. So if we look at numerical columns, we basically, so what we use matplotlib, that's with PLT is basically matplotlib, and basically plotting matplotlib and figure size, like size of the figure, like 17,5 centimeter and such. Again, I mean that the unit can be decided, right? And then I'm iterating over all of these numerical columns like one by one, and then I'm plotting them one by one, and then plot can be seen here, right? And then when I look at my data, I'm also using describe. So when we want to use Pandas data frame has this module called describe. The describe module describes your numerical column. So if we just apply train df bracket numerical columns, so all those numerical columns dot describe, so all those numerical columns will describe. What it will describe? It will describe what are the counts in each of what are the total counts in your data set, right, of all these numerical columns. What are the mean, what are the standard deviation, minimum, 25th percentile, 50th percentile, 70th percentile, what is the maximum in your data. So in your each column, right, in this case if I say applicant's income, in the applicant's income there are 614 observations. As we know, there are 614 entries in my data. The mean is 5403. That means 5400 is the average monthly income for this for all among all the applicants. Standard deviation is 6109. That means from mean, the deviation that is there, that means the minimum value, that is the left extreme value, and the right extreme value from the mean is plus minus 6109. Similarly, minimum is 150, 25th percentile is 2877, 50th percentile is 3812, 50th percentile we call it something like median or something, right? Similarly, 70th percentile is 5795, and maximum is 81,000, right? So that's how your data is there. You see how much is the difference? The mean is 6403 and your maximum is 81,000, right? So some is the average income here is 5,000 and the maximum income is 81,000, right? So in those scenarios, do you think mean is the better way to look into it? Because looking at mean may give you a bias result, right? That I'm getting a mean of 5,400, but that mean income is being biased by the maximum income, because mean will include all the incomes, right? And when you take the maximum income along with all other incomes, the overall mean income will increase. But if you remove this maximum income, the overall mean income will reduce significantly, right? So mean takes into consideration the extremes of the data set as well, and those extremes actually impacts your average or mean, right? So making sure where you need to take mean and where not is also a good way of using statistics in your data, right? If your data is normally distributed, that means it's following a bell curve like this, right? That means your mean is in the middle of your data, right? That means if I have 100 data points, right, the mean is somewhere around 50 or 51 data point, which is also the middle of the data, all the observation that I have, then that's a good mean, right? Because the distribution is uniform, then you can take mean into consideration. But in this case, as you can see from the curves also, and as you can see from the data that you got from the describe, the mean is being dragged towards the maximum value. So maximum value is impacting your mean in this case. So if we look into the box and whisker plot, so box and whisker plots are nothing but they gives you the idea about where does your data lie, right? So box and whisker plot has 5 variables to look at. So the lower extreme is your minimum, the upper extreme is your maximum, the extreme between these two lines is basically your 25th and 75th percentile. So the lower line that you see is 25th percentile, the upper line that you see is 75th percentile, the middle point that you see, or if you see that there's a line in the middle, right, this line in the middle is basically your mean, or basically 50th percentile, right? So you have minimum, 25th percentile, 50th percentile, 70th percentile, and maximum, right? and any value that is lying beyond your 75th percentile, that means this line, any value, any points that are lying beyond the 70th percentile are outliers, right? So those are outliers. That means they need to be removed from the data to make sure the data becomes as close to normal distribution or uniform distribution as it can be, right? So if you remove these outliers, that means removing numbers like these max 81,000 or 41,667 and such, right? Because these numbers are impacting your data or impacting your mean. So if I remove these numbers, this whole box and whisker, this whole whisker will shift to, it shift in the middle somewhere. Possibly these values, y-axis will also reduce, because now it won't have these outliers. So it will be like 0 to 0 here and 10,000 at the top, and then your box will be in the box will look like this. So your box will, you can call it as zoomed out. The box will zoomed out. That means you cut your box from 10,000, and now it's basically shown as normal distribution. So what you can assume is, the curve something like this. So you have a curve like this, as you can assume in your data. That curve is almost near to normal distribution or uniform distribution in that case. Next, this is for loan status, and this for loan approval people, loan approval applicants, and approved loan applicant income. This is non-approved people applicants income, right? And even you can see that the 81,000 guy is in the non-approved area, right? That 81,000 guy who has the maximum applicant income comes in the non-approved area, right? So, and he was not given the loan for some other reasons, right? So it's not necessarily that this guy has a high income rather than my rest of the applicants, I should give him the loan, right? That's not just that should not be the only way or right way to approach the thing. Similarly, if you look at co-applicants income, this is how the distribution shifted out. Now the box has been shifted out close lower down to the minimum side on near to the 0, because there are other areas which are basically impacting a lot in those cases. Similarly, the loan status for loan amount is basically somewhere around 0 to 700 and such, and I can still see some outliers because it's beyond these lines or these outliers. If I remove them, my distribution will be somewhere around 100 to 200, and it will be good enough distribution, right? So this understanding I got from my data, right? So for numerical column, there's no significant relation to loan approval status. Yeah, that's true, because I'm not seeing any kind of, see if you can see even for cases where the loan is approved, even for the cases where the loan is not approved, the income distribution almost same, right? The graph for both of them almost same. Blue and green are almost same graph. I can't see any significant relation in the loan approval status for these numerical columns. So they are almost following the same pattern for both approval people and non-approval people both. Pre-processing. So input data need to be pre-processed before we feed into the model. Following things need to be taken care. So encoding categorical features, imputing missing values. So categorical features like this urban, rural, and all of those male, female, no, yes, these has to be encoded and converted to a numerical value, because that's what my data will take into, right? It won't take the English features. So I need to convert into encoded values, that numerical values that could be that they could take into, that my algorithm can take in and then process. So first step is basically in the pre-processing data is encoding the categorical features. So I'm using, there's an API called pandas.getDummies, which I'll get, which will give me dummy numerical values in place of these, these categorical values. So what is it? What I mean by dummies is nothing but, if I say married, there's either no or yes, right? There's no something like maybe, like kind of like that. There's no something like maybe. Either no or yes. So in that case, I can assign no as 0 and yes as 1. That's a dummy value that I put it into. Similarly, gender could be either male or female, or other could be anything, right? So I can put as like 0, 1, 2, or -1, 0, 1, sort of like that. Those are like dummy values, and so on, right? So if you see, so I can see that gender male I put it as 1, then gender there may be, then married yes or not. So similar. So dependents 1, dependence 2, dependence 3. So what has happened is for each loan ID, I created a new column for such cases. So if it's married, yes, then it's 1. If it's not, then it's 0. Similarly, dependence 1, no. Dependence 2, no. Dependence 3 plus, no. That means there's no dependent for this particular loan ID, loan applicant ID. So I've just divided into 3 different columns. So just create what this do is get dummies do. It creates these columns, dependent 1, dependent 2, dependent 3 automatically. You don't have to do it by manually or something. Just do it automatically, and it will create like this. So that it create for every category, it creates a column. So if there's a category called dependence, number of dependents that equals 1, number of dependents equals to 2, number of dependents equals to 3 plus, it will create a column or category out of it. It will that category will become a column or attribute, and then that column attribute can be 1 0 1 0 1 0 anything, right? So you can basically, that is how get dummies works. That is one way of doing things. That's not the only way. That's one way of doing things. The other way of doing things like one-hot encoding or label encoding or using PCA and such. So there are other ways to do things as well, right? Similarly, split features and target variables. So I know my target variable, right? So always in a data set, something is need to be predicted and something has to be used to do those predictions, right? So if you look into our data set, this one, I'm using all of these columns to predict what? Loan status. So what I'm predicting, ultimately loan status, either is 1 or 0, right? For the cases where the loan status is not there. So I'm predicting loan status using what? All these columns here. You know? So technically what's happening is, in this case, I'm dropping from a train DF encoded. I got this train DF encoded from here, right? Using that train DF encoded, which I'm putting my X and Y, right? Y is basically what? My loan status. Is it yes or no, right? And X will be my all other columns apart from my loan status column, right? So that will be my X. So X is my feature and Y is my target variable, right? Then what I'm doing is splitting data into training and test data, right? So I'm using scikit-learn model selection API to get the train test split module to do the train test split. So we have learned right here, right, that on the steps that, you know, once you do, we have done all. So what you have done till now, let's see what you have done till now. So we have done data pre-processing, right? We have created a decision status variable 0 1 and such. We have encoded that variable. We have selected columns. We have selected all these selected columns which we're going to use. We have encoded the gender and all those things, and now our data pre-processing step is finished. Now what we are starting is, we're starting model building. We're dividing our data into train and test and setting the split ratio to be 70%. That means 70% should be train, 30% should be test. So I'm trying to do that here only, right? I'm trying to, using the scikit-learn model selection API, I'm trying to import train test split. And using this train test split, I can split my data into training and testing. So what is happening is, for each feature, I will have a train. For each feature, for each X, I'll have train, X train, and X test. And for Y, I'll have Y train and Y test, right? So it's nothing but it just simply is like, chopping up my rows. So if I just chop my rows from here, what I'll have, right? This will be my X train. Like all these columns will be my X train, and this Y status column will be my Y train. Similarly, if I look at below this 0, these 3 columns, whatever will be there will my X test, and this loan status column will be my Y test. So this is what is happening here. So X train, X test, Y train, Y test, using train test split, X comma Y. Test size is 0.2. What is 0.2? This 20% that we are talking about, 30%. So 70% is basically split ratio. That means 70% is train, right? And 30% is test. So 30% is 0.3 is test. In this case, I'm taking 0.2 as test, right? This parameter can be changed depending on the performance of the model that I'm getting in after changing this parameter. So this is not a hard and fast rule. I can put a 0.2, I can put 0.1, and so on, right? Depending on whichever giving me the best results. So I'm using 0.2. That means 20% will be my test and 80% will be my train, right?
And there are some of the parameters that is being required. Similarly, random state 42, you can put a random state as 42. That means I'm putting it as whatever the output that I'm getting from train test split, I should get the output every time I run this code. What happens is this train test split happens randomly, right? So sometimes it will train these first, let's suppose 7 rows, and then the split on based on these 7 rows and split on 0, and basically, or split on this rows. So the first 7 will be on train and the next 3 will be on test, right? In the next time I run the code, what happens is it will take the first 4 and will take the last 3 in train, and will take the middle 3 in test. So this keeps on changing. So this doesn't keep on changing. What I do is I put random state as some fixed state, that is 42 or any random number. This is not 42 is like some other parameter. You can put 21, you can put 20, anything. Just to make sure that every time the split happens, it happens the same way, right? So once you did the split, you are now need to look at the missing values. So how do I handle the missing values? So handling the missing values is basically called data imputation, right? So all these missing values that you have in your data needs to be handled, and the procedure to handle these missing values is called data imputation. So data imputation is a mathematical process. Technically, is a statistical and linear algebra combined process. In the backend, a linear algebra and statistics both are happening, right? You could use a statistical approach to fill your missing values or drop them, or you could use a linear algebraic approach to fill your missing values or remove them, right? Or predict those missing values. So there's a whole class or a whole lecture set it up just for data imputation, to understand how do we handle the data imputation, how do we handle the missing values. But right now here we'll use scikit-learn simple imputer. So scikit-learn, sklearn is basically a library which is basically has all those machine learning algorithms, all those data processing libraries built in inside it, which you can use it directly into your code. So you don't have to write code from scratch for every little thing you do. You can use a library or module, and you can just use it in your code and then work it around, right? So in this case, from scikit-learn.impute, you're using simple imputer API or module. That simple imputer module will take just one parameter, like how do you want to impute your missing values. So if I have missing values in one of the columns, what I want is, let's suppose this column has missing values, right? So 0 is not a missing value, it's just that the income is 0. But let's suppose there's a missing value, that means there's no income mentioned, neither is 0, neither is any value. How do I basically impute or fill that missing values, right? So I'm saying the strategy should be mean. That means mean imputation. That means I'll take the mean of this column, let's suppose mean of this co-applicant column, in co-applicant income columm, and with that mean I'll fill those missing values. So using that strategy, I'm saying and I'll do a imp.fit on the x train. That means all the x features, and fill those missing values using mean imputation. Similarly, then imptrain.transform. That means it will now fill those missing values. First, I did the fit and transform. Fit and transform is generally two methods that is you do while training your model, or any kind of imputations as well. So fit will basically fit that algorithm that is there in behind a simple imputer into a data set, and transform will execute that algorithm and get the output values into it, right? And then transform.xtrain will give me the will fill all these missing values that are there in my all the different columns or any rows. So I don't have to find it out, but it will fill it by itself. How did I find it out if there are missing values? I already did from the past. So in this case, it says all of them are non-null, right? But what I see is dependence has 599 counts. My total entry is 614. What happened to the rest of the 15 counts, right? So I need to figure out how I can fill this, right? Similarly, if I look at co-applicants income, loan amount, 592 has given me the loan amount. What happened to the rest of the other entries, right? 21 or 22 entries, right? So I need to fill those missing values as well, right? So I need to find out I'm filling those missing values using simple imputer or mu imputation. For xtrain, xtest, both. All right. So I fill those missing values for xtrain and xtest. Now, what I need to use is, now I need to fit my data to a machine learning model. I can use any of the machine learning model. I can use decision trees. I can use, I can use random forest, or I can use random forest classifier, decision tree, logistic regression classifier, anything. Why I'm using these algorithms? These are supervised learning algorithm, right? So what is supervised learning algorithm? Supervised learning algorithms are those algorithms a data and the output of the data in your data set. That means I have this data, right? Output of the data is loan status. Loan should be provided or not provided. That means the output of the data as well as the features of the data are being provided to you. That means that is a supervised learning. There I can implement a supervised learning algorithm because the data set is this way. What if my data set doesn't have this loan status? I don't have any information about the loan status of the past entries as well, or future entries. So anyway, I don't have. For past entries, I don't have any information about it. Then I don't have a target variable. I have only features or predictors in the features or predictive vector variables or features. So I can't basically use a supervised learning algorithm here because I have data. I don't have the target. How do I basically supervise it? Right? So I have to use an unsupervised learning algorithm like clustering or nearest neighbor or such kind of approaches. Since I have supervised data with me, I can use supervised learning algorithm like decision tree, random forest, naive Bayes, logistic regression, and such. What are these? These are all classification algorithm. Why we need a classification algorithm? Because we are classifying our observations or loan applicant's ID, whether there is 1 or 0. We're classifying it into 1 or 0. That means loan should be given or not. That means a binary classification problem, right? So I'm basically using decision tree classifier using scikit-learn API. Again, scikit-learn.tree has this API called decision tree classifier. I can use it and I can fit into my data to get the output. So similarly, I can use model selection for cross-validation score metrics to get the evaluation metrics like accuracy score or F1 score. Now, there's something called, cross-validation. What is cross-validation? So I'm using CV equals to 5 or cross-validation score and such. What happens is, usually we do a cross-validation to determine if, something, just to make sure that I don't distribute my data in a way where it become biased towards one particular observations and become unbiased towards other observations. So I do a cross-validation, which is a resampling method that uses different portions of the data to test and train a model on different iterations. So what does this mean is, just like I told you, right? When I do a split, it will first pick up, first seventh for train and next third for test. But next time I run that code, it will pick up first four for train and last three for train and middle three for test, right? So what cross validation do is basically create a multiple scenarios of train and test data sets, right? Train and test samples, where for let's suppose if I have 10 samples, it will take the first 9 for first case. It will take the first 9 as train, and let's suppose the 10th one as test, or first 7 for train, last 3 as test. Similarly, first 4 for train, last 3 for train, and middle 3 as test. Similarly, last 7 as train and first 3 as test. So just take these multiple scenarios and it basically tries to calculate a cross validation score, right? So basically for every train and test, it will basically test my model, decision tree classifier model, for these different combination and permutation and combinations. And for each combinations, it will try to get the predictions for my, or train my model into, right? Once I train my model into multiple all of these, or predict my model into all of these train and test, then combined together we find the most optimum combination. That we say, okay, I want to create 5 combination. I'll create CV equals to 5. I'll say this combination is the best combination. Let's use this combination for training our model because I'm getting the maximum amount of accuracy from it. So that's why we do a that's why we do a cross validation for our data sets. So what happened here is I initializes the decision tree classifier module. Then I used initialized tree underscore CLF, and I did tree underscore CLF dot fit into X train and Y train. X train and Y train I already got it from there, right? So I'll basically training my data on the training data set, which is X train, which is this all these features, and Y train, which is my loan status. And then I'm fitting it, and then after fit, I'm trying to predict it on the Y prediction for X train. That means I'm trying to see if over the training set what I'm getting the accuracy for, right? So what I'm trying to do here is you used to learn something in your, let's suppose, class 5th. When you were in class 5th, you learn something on in the chapter 1, right? And then your teacher asked something from the chapter 1 to you, and then you give the answer, right? So this is what is happening. I'm asking my model to learn everything in chapter 1, right? And then I'm asking my model to also predict what is this part in your chapter 1. Tell me the answer of it, right? Like filling the blanks or such that your teacher used to ask you. So this is what I'm training my model on my training data set. I'm also testing my model on my training data set. If I'm doing that, my accuracy will be what? 1, because it's a machine, right? You might forget something, but a machine won't forget, right? So my training data set accuracy I'm getting is 1. That means 100% accuracy, right? Training data set everyone score also adding 1, because that means 100%, because I'm training and testing on the same data set. Just data set the data set which I tried to learn my model from, the same data set I'm trying to test it over. So it will give my 1, accuracy is 1. But if I test it on a test data set, the accuracy might not be 1. It will be less than 1 in that case. It will be 1 in very rare cases, right? Usually for the best possible scenario, it will go to 99% or 99.5% and such. But for getting into 1, it's basically in a very, very, very rare scenarios, right? So for those test data set, I'll do the testing as well. What I'm getting in my validation score is, on the cross validation score, I'm doing a 3 CLF, X train, Y train, CD equals to 5, score is F, M macro, and mean. So what I'm trying to do is I'm creating a cross validation, and I'm calculating the mean of all the cross validation for all the 5 scenarios that I'm doing the cross validation for, and then I'm getting the mean F1 score and mean accuracy. In that case, I'm getting the mean F1 score 64% and mean accuracy as 70%, right? So now my accuracy has changed once tried out different combination of training and testing using cross validation. So for one combination, it gives me 1, but for other combination, it might have given me 50% or 60%. That combination meaned out to be finally 70%. So that's why I'm getting a 70% accuracy. Now we can see from the above metric that training accuracy is greater than the test accuracy, right? So what happened here? The training accuracy is greater than the test accuracy. That means my model has overfitted my data. That means what is overfitted? That means if my model is having, let's suppose, an S curve or any kind of curve, exponential curve, like, or data is exponential curve. My model has also learned that this data is exponential curve when I test it on my training accuracy. That's why my training accuracy is getting to 1 and greater than my test accuracy. So the overfitting is a very common problem that the model tried to wrote it. It's like a rote learning, that you wrote something from chapter 1 that you taught that has been there in your class 5th, and you vomit it into an examination. That's everything you wrote, right? But you didn't understood anything. There's a difference between understanding something and then rote learning something. In the rote learning, you just you memorized everything and then you spit it out. But when you understand something, you don't have to memorize everything. You understood the basic fundamentals or concept of it, and then you try to answer your questions in your exams based on what understanding that you had, right? That's how you understood your whatever the chapter that you read. So when your model overfits, that means your model did a rote learning. That means it memorized everything, and when it comes to the test, when I give him something similar but not the exact same thing, it will fail, right? I'm giving something similar, some new observation is coming, it's something similar but not the exact same thing, it will fail on that observation. because it's done a rote learning. That means memorize the same thing. So if you given the same thing, it will do good. If you give something even closer to it, it won't work. So overfitting is a bad to any of the machine learning problems. So testing accuracy with default settings for decision tree classifiers, hence the model is overfit. We'll try some hyperparameter tuning. Note this term hyperparameter tuning, because this is something is the majority of the job of a data scientist. You will build your model, you will do everything, but if you're not smart in tuning your models are of no use. So hyperparameter tuning is like tuning your parameters like your CV, this value like 5, or your splitting value like size 0.2 to 0.3 or 0.4, anything, right? Or any of these values, right? So tuning these parameters and then trying to retrain and get the output is basically is hyperparameter tuning, right? Okay, so there's a question here, which is, did the step of reading null data rows happen or was not important in this notebook? Oh, simple impute chooses exactly the co-applicant as another variable. Choosing for training 70%. Okay. So in this case, what happened is, see, when you say imputing, handling out missing values, the handling out missing values and null rows shouldn't always be done by removing them. That means filtering out null values. That's not the only way. The reason being, what happens is, let's suppose if you have a lesser data set, smaller data set, let's suppose if you have 10,000 data points. In 10,000 data points, if you try to remove, let's suppose I have 5,000 rows or 6,000 rows which have one or two null values in each of the column. Let's suppose in one of the observation I only have null values in my loan amount, right? So this value, you can see this null, right? Only have one value in my 10 observations. There's only one value, right? Then it is fine, I can move it. But what if in my 10,000 there are 6,000 rows which have in loan amount there's null value, right? I can't drop all those rows, right? If I drop all those rows, my data set will reduce to like 10,000 to 4,000, right? Which will be difficult because I don't have enough data set to train my model. My training accuracy will be lower, or my test accuracy will be lower, or my model is not optimal, right? My model is not trained appropriately because it doesn't have enough data. So instead of removing null values, what I did is I imputed them. So I basically try to fill those null values by using simple imputer, which is a strategy where I'm using a mean imputation. That means I'm trying to calculate the mean of that particular column, let's suppose loan amount, and I'm filling this missing values with the mean. That means since my rest of the observation that I see in the data is basically having this mean, that means I'm assuming that this particular empty cell maybe this value, because I imputed with a mean imputation. There could be multiple imputation also. I could use median, I could use mode, I could use nearest neighbor approach. That means I'm synthetically creating those values. There's so many algorithms for data imputations, but I'm just trying to give you a gist about how I'm doing using a mean imputation, right? So in this case, I haven't dropped that null value because it has only one loan amount doesn't have is empty. Rest of the observations are there, right? For this loan ID 002. I have rest of the application, rest of the observations are there except the loan amount. So what I could do is impute that particular value, right? Instead of dropping it. If it's too many of the observations that are not there, then I have to predict for so many columns. Instead of predicting, I'll just remove it. So how do I decide this? If I say that, I have total 13 columns and I'm saying 8 or 9 or 10 of them, or maybe 70% of those columns are empty, I'll just remove that row. Because instead of predicting so many, values, which basically hypothetical values, not the actual data, I will basically be risking my accuracy. So I'll just remove it. But if there's one or two values, I'll use mean interpretation to predict it, right? So that's basically the approach that I've taken in this case. How simple impute chooses exactly the co-applicant income as another variable. Yeah, so basically you try to use it for, so what you do is it when you apply simple imputer, right? And when you apply it into imp is this one, right? Imp.fit xtrain. So when I do xtrain, imp.fit xtrain, it will take all the, all the numerical values. So whatever be there, right? I have applicants income, co-applicants income, loan amount. It will take for everything. So it will check for co-applicants income. It will basically see where the missing values, fill it with the mean imputation. It will check for loan amount, see where the missing value, fill it with the mean imputation. So that's the automation that you get from Python, right? You basically have to use just simple imputation. You don't have to do it for every single column. You just to fit, you should put it, do im.fit xtrain, and it will find out the missing values and it will fill it for you. So it's just that you don't have to do it for every single columns there. Then how much data was chosen for training? So like I said, we are basically using 0.2 test size is 0.2. When test size is 0.2, that is 20%. That means 80% of the data set is used for training in that case. If it's 0.3, that means 30% of the test size. That means 70% is data is used for training. So in this case is 80%. Let's move ahead. So once we have this, so how do I train this? How do I do pointer tuning? So let's try tuning the max depth of the tree, right? So what happens is a decision tree looks like this. So you have a credit history less than equal to 0.0425. If this condition is true, then move here. If it's false, move here, right? This is how decision tree classifier works, right? If I use loan amount, if this is true and loan amount is less than 488, right? How many values are there in those such cases, right? If it's there, if this is true, then go here or else go here, right? Then if in this case loan amount this, co-applicant income is less than this, then go here, otherwise go right? So this is how the decision tree takes decisions and classify while this applicant should be 1 or 0 in terms of loan status, right? So this happens in the back end, and it happens using Guinea values or Guinea samples. So what is so this to understand this, you need to understand how decision tree works, right? So I'll just give you an idea about decision tree classifiers. So generally what happens is a sequence of queries or tests are done to basically see if a certain previous test influence the test that is performed next. So if I'm in this case, I'm testing credit history, and then I'm seeing based on this credit history, if it's true, then I'm checking loan amount, then I'm checking co-applicant income, and then so on, right? And this is basically what we are forming is a tree, right? This is like a tree that we are forming. So there's a parameter inside a decision tree algorithm called max depth of the tree. That means we are basically trying to get the how much depth I should go into while I'm basically training my while I basically train my decision tree classifier. In this case, the depth gone into is like 1, 2, and 3. So that max depth is in this case is 3. I can take the max depth to more levels and see if that max depth is going to help me get a better idea about the decision tree classifier, or better idea about the output from the decision tree classifier. So I can modify that parameter. Let's suppose from max depth 3, I put it max depth 5 or max depth 8, right? And then I see, do I get a improvement accuracy or do I not in such cases? So this is how basically the decision tree is trying to do it, and do it on Gini index. And so if I say that in this case the sample is 491, then when it's true, in this case the loan amount less than equal to this sample, it comes to be 67. For those cases, if it's true, and if the co-applicant income is less than 8115, the sample is 66. And if it's true, then I'm getting a 65 samples, right? So in this case, 65 samples I'm basically reduced to with end of these conditions, right? So, and similar for other cases, right? So technically what happens is it tries to decide based on the Gini index, right? So what is Gini index is, or there's something called entropy and Gini index in decision tree. So Gini index is basically or something called Gini impurity is basically calculated by subtracting the sum of the squared probabilities of each class from 1. So basically there's a certain formula that is used to calculate the Gini index. It basically tries to calculate that information gain, or so these are all technical terms that you use while you basically try to learn the decision tree classifiers. Right now, since this is not a great decision tree class, so I'll just give you an overview only. Won't go much into detail. If you don't understand, that's fine. This is just a gist of it. So it basically tries to use the Gini index or information gain to split a node. That, if I say that, it's basically how, if the node have a multiple classes, is impure, whereas node having only one class is pure. So basically what happens is, in this case, if I'm saying that this node can be classified, this how do I decide that, credit history should be taken first, not this one, right? So credit history should have a high amount of Gini index, such that it could be decided as the topmost node, or what you call as a pure node, right? And then based on the and based on that, then I decide based on Gini index what should be taken next, whether it should be loan amount or applicant's income as such, right? And based on that, what should be taken next in such cases. So the Gini index value keeps on changing based on how the split happens on the node, right? So this is basically how internally Gini index decides which is the most pure node and which should be used, which of the features should be used for division or checking of the conditions, and then the division of that condition to go around in depth inside the tree, right? So all of that basically was internally inside your decision tree classifiers. We'll go in deeper once we study on that particular front, but right now you can basically move with this understanding. So what I'm trying to tune here is max depth of each tree. So in this case, what I did is I iterate over each of the values of max depth, and then implement decision tree classifiers, then fit it, train it, predict it, calculate the accuracy score. Accuracy score, how does it come? It came from scikit-learn only. Scikit-learn metrics, accuracy score, F1 score. So these are like evaluation metrics. Scikit-learn metrics is an evaluation metrics based API. So I basically calculate the F1 score, cross-validation score, cross-validation validation mean accuracy, and then try to predict these values and tune it, right? So this is how the graph actually looks like for all of these 20 observation or 20 depth that I tried my model into. So what I did here is I use a parameter called max depth that is there in my decision tree classifier. So decision tree classifier has this parameter called max depth. I put that different values of max depth, experimented with different values of max depth, and then I plot a curve like this, right? So at max depth 19, I'm getting the highest amount of accuracy in training, validation, training, F1 and such, right? So obviously the lower the depth that you go into, the more it's clear for the model to understand that should be given the loan or not, because it's getting more data, more observations, and more time, more decision points. So higher the max depth, I'm getting a better amount of accuracy. So this is how the plot comes out to be when you use a max tune over the max depth parameter here. So I plotted this graph and then basically get the output of it. So from this I can see that hey, if I can use max depth around 17, my model will be I don't have to process that extra max depth, so because it will use extra resources for it, and it is a good enough way to get the almost maximum amount of accuracy, because accuracy is near to 95%, 98% in case of max depth 17, right? So that is how I tune that max depth parameter, right? From there I'm getting at max depth equal to 3. If I keep the max depth equal to 3, I will get the maximum test accuracy and F1 score to be 80% and 70%. But when I visualize that max depth equal to 3 parameter, right, which I used above, I basically get that. So I use this code to basically use a max depth equal to 3, and then I plot a graph. This is how max depth equal to 3 looks internally. When I put a max depth equal to 3 parameter, that will go to three levels only. So 1, 2, and 3, and then it will say that this is how your max equal to 3 output will look like, and you'll get a test accuracy of 80% and 70% in your max depth equal to 3. So when you do max depth equal to 17, this tree becomes very large, right? And it will take longer time to train your model. So make sure of how to use this parameter wisely, right? From the above tree, we can see that some of the leaves have less than 5 samples, right? So obviously, like if you see these leaves, like 1 sample, 3 samples, right? 1 sample. So some of the leaves have 5 samples, hence our classifier might overfit. We can sweep hyperparameter minimum sample leaf
to further improve the test accuracy by keeping max step to 3. So technically what's happening is, here I've used parameter called max step, since I know that there are some less samples that I'm getting when I split it with max step to 3. So there's another parameter called minimum sample leave. I could use minimum sample leave as another parameter to basically train my model, and max step equal to 3, minimum sample equal to sample leave. And basically I iterate over sample leave from 1 to 80 with 3 distance. That means 1, then 1, then 4, then 7, then 10, and so on, right, up to 80. And then I tested my model into. When I test my model into, I'm getting this kind of graph, right? So for if I look into this particular model, I'm getting validation accuracy of maximum at somewhere around 52, and it remains constant from 19 to 52. So if I use somewhere around minimum sample leave to 35 or something, like somewhere in the middle, that will be a better to improve the test accuracy, because I'm getting this particular area. So I use the minimum sample leave values of around 35, which is in the middle of constant values of between 19 to 52 to get the minimum sample leave value. So maximum that equal to 3 and minimum sample equal to 35 will give me a better accuracy. So I can see right now my test accuracy is improved from 80 to 85%, right? F1 score is improved from 70 to 90%. So I can get a better accuracy when I tune these parameters, right? And my cross confusion metric that I was talking about is basically this. This is what, when we look at the last part, confusion metric for actual values and predicted values. This is the confusion metric. So 0, 1, 0, 1 in row and columns. So these are the predicted ones, and this is the actual one. So what I mean is, in this case, the actual was 21, and the predicted was actual and predicted. Where does it match? Is 21. 21 samples. Similarly, my loan prediction was 0 actually, but I predicted as 1. So how many cases happen in 17 samples, right? Similarly, my actual was 1. That means I should give the loan, but my predicted was 0. That happens in one case. My actual was 1 and predicted was also 1. That happened in 84 cases, right? So that's basically my confusion metric that gives us the idea about what was the actual value and how much, what did my model predicted to, right? So there are misclassifications that also happen. In this case, what are the misclassifications? That my predicted actual value was 0. That means I should not give the loan, but my predicted was 1. That means in 17 observations or cases, I have given the loan, which I'm not supposed to give. So these are called misclassifications. You can see the majority of the misclassification happen because the loan reject applicants being classified as accept, where in this case loan reject applicants are 17 and they're classified as accept, which should not happen because it will impact your business or the bank's business. So let's look at, and so in this case what I can do, I could either improve my model further by improving these parameters like max depth or minimum sample leave, or I could use another algorithm. So in this case I've used random forest classifier, which is another algorithm apart from dysentery classifier, which can basically give me a certain level of accuracy. I'm getting at 86% train F1 and 79% and 69 and 79% validation accuracy. So train, test, and validation. So that you just assume that validation is like training. Let's suppose you get 70% train, you could take 20% test and 10% is validation. So validation set is just to give you the idea that how does your model performing, and based on the validation accuracy, right? So it's just generally been divided this way, right? If I'm not explaining validation accuracy previously. So in this case, I can take random forest test data evaluation, and I can see that particular idea, right? Similarly, I can use logistic regression model, and using logistic regression model, I can do the same thing ever again. And I can get the idea that, I'm getting a test accuracy 86%, 90%, almost similar to my decision tree, not much impact, right? So I can do these keep on experimenting for each model, and then, try to determine my, value or output, right? So that is how, you're trying to predict the loans. So what is happening is, in this case, I can basically use this trade notes, pred value. My pred value will contain all my loan predicted
predicted values. So this here I only test the accuracies. How do I test the accuracy? There's a predicted value only. So that Y prediction will give me the predicted value of loan for the test data set. So they'll give me, here's Y. So my predicted value will be either Y or N. That means yes or no. In this case, if it's N, predicted value is N, then the predicted value could be N or Y, anything, right? So Y pred has this predicted and actual value ka data. Sorry, mostly the predicted value ka data, and you can check it from the actual value, and that is what we are doing here. So this is how you basically approach your loan prediction model. Similarly, you can do it in R and Python both, and get that output on approach. So I hope you get the idea about total complete data science project or approach towards solving a problem, and based on it you can decide how basically which algorithm to approach towards solving a data science problem or building a machine learning model, and keep on experimenting on data and algorithms both. So there are only two ways to improve your model. Either you improve your data set, that means you do a better pre-processing, use better features, and all that, or you basically change your algorithm and try multiple algorithms, and or try to hyperparameter tune those algorithms to get the best accuracy. And thank you all for attending the session. That is all about it for today.